So today my talk is also non-technical. So just introduce something which is interesting to discover the causal information from the purely observed data. So first of all, I'd like to introduce you three different models: the physical model, an overview of the three models: physical model, causal model, and the statistical model. So a physical model usually is a set of coupled differential equations, and it offers insight of a physical system. For example, it can be used to make predictions if there's some change on the system. If we put some intervention with a physical system, we can still make predictions. So, but the physical model usually is very complex. It's very difficult for us to learn the physical model from the data. And usually a physical model needs human experts to come up with it. So on the other hand, what is the statistical model? A statistical model usually is a joint distribution. It describes the statistical dependence among different components of a system. That's why we can make predictions. However, it cannot be used to make prediction if there's some change, if we do some intervention into the system. Okay. A good point is that for a statistical model, if we have data, those distributions can be learned, which on today the keynote Scott introduced us as some very exciting method. In the middle, I would like to introduce that which is a causal model. So a causal model it describes the causal relationship among those components in the system. It is less complex than a physical model, but it brings more information than the statistical. If there's some change, if we put some intervention into the system, by using the causal model, we can still make predictions. And also a good point is that although it cannot provide us some physical insight, but a good point is that with some mild assumptions, those causal model can be learned from the observed data. Okay, and today we will introduce you some typical method which will discover the causal information from data. So also I'd like to further introduce you that causal model is more useful than statistical model for some application. So here I would like to illustrate to you two examples. The first one shows that there's a high statistical dependence between having breakfast every day and keep fit. Very high dependence. So we can make predictions by if we observe someone usually have breakfast every day. If I have breakfast every day, then this person may unlikely to be fit, so we can make the prediction. On the other example is that there's also a high dependence between the chocolate consumption of a country or a region with the number of Nobel laureates in the country. Okay, so also we can make predictions. We can observe if how many chocolates a country have been consumed to make a prediction how many laureates they have. But can we do some interventions? For example, if we want to have more laureate fellows, can we Nobel laureates, can we just encourage our people to eat more chocolate? And if we want to be slimmer, can we just eat breakfast every day and then we can achieve that? Obviously not. The reason is that make predictions, we can make use of the statistical dependence. But if we want to make intervention, we have to make use of the causal relationship. So there's some causal structure behind. For example, it is a common cause of a healthy lifestyle, which will result in you have breakfast every day, and also you have you keep fit. So if you want really keep fit, you have to have a very healthy lifestyle. So we have to. It is important for us to discover the causal relationship from a system. Okay. And now also many very famous leading researchers are promoting this causality for machine learning. For example, Judy Herr, who mentioned that lacking causality is the major block of the machine learning to have the human level intelligence. And also Yoshua Bengo mentioned that the causality is very important for the next steps of the progress of machine learning. And now I'd like to introduce you the causal models. There are two popular causal models in the community of causal discovery. The first one is the structural causal model, which is a set of equations. Here, those x represents the variables, and the f is the function. DC here represents the direct causes of the variable xi. And the n here represents exogenous noise. Usually for different n's, they are independent to each other. And a second model is a causal graph model, which is a directed cyclic graph. That maybe a lot of you are familiar with this term. And the edge represents the causal direction. And to compare those two models, it is obvious that the structured causal model contains more information than this causal graph model, because this function can describe the strength of the causality. With those causal models, and how can we discover those causal models? How can we identify those causal models? So the gold standard is to do a randomized experiment. I think this is one example which can be easily understood by almost everyone. And I think just in the morning's talk, there's also a very interesting examples. What's the factor that's caused the change of the waters, the climate, the water color, and there's many interesting applications. So here I would like to show one example how to analyze if the higher education is a cause or not for the income. So to do so, if we want to do randomized experiment, we have to recruit a large number of high school students, and then we randomly divide them into two groups. And for one group of them, we send them to higher education, and for another group, then we directly send them to the job market, and then we track their income throughout their lives. And after that, we can do some analysis to say really if this higher education is a cause for their income or not. But obviously it takes time and it's costly, and also it may have some ethical issues. And for many other interesting questions, we may not even be able to do those randomized experiments. Luckily, now in the machine learning community, if we have data, okay, with some assumptions we will show you later, we can design machine learning algorithms to recover those causal models. That is really interesting. The first setting, so later we'll show you two settings to discover the causal model. One setting is that all the variables we have observations. There's no latent variables. So this is the indicate. And for this setting, we will introduce you several representative methods to discover the causal relationship among all those observed variables. Another setting is that we have some latent variables. This is more realistic. Usually, there's a lot of latent variables, and we'll introduce you some method how to discover the causal relationship. And here, the first algorithm I want to introduce you is the PC algorithm, which is very famous, proposed by two persons, Peter and Clark. So the algorithm requires two assumptions. Actually, the one assumption is the Mark property assumption. It assumes that there's a relationship between the separation and those conditional independence. And another assumption is the faithfulness assumption, which is in the other way is shows the relationship between those conditional independence to this separation. So I'm not sure if you know the concept of separation. It is a concept in the graph theory. Okay, for a graph, for example, for a deck, if we have three set of variables A, B, and C, and we say A and B will be separated by C, if for each variable in C, there's two conditions. One is that each variable in C will make up either three different structures. We call this, for example, X k minus 1, X ik to ik plus 1 as a chain structure. And also this is a chain structure in another direction. And for this structure, it is a fork structure. So for those structures, the variables in the middle has to be contained in the set C. And the second condition is that there's another structure. This structure is called a glider. For this variable in the middle, this variable cannot be included in the set C. If those two conditions are satisfied, then D will separate the set A and the set C will deseparate set A and B. With those two assumptions, okay, there's one-to-one mapping between this separation and those conditional independence. So the PC algorithm actually makes use of this one-to-one mapping. For example, given this observed data, we can use statistics to calculate if there is conditional independence or not. Okay, so we can recover those conditional independence information. Given this conditional independence information, we can infer those deseparation information. So given a deseparation information, we can reconstruct this causal graph, which will entail those deseparations. So for this PC algorithm, the causal graphs restricted are not unique. For example, given a set of conditional independence, or in other words, given a set of deseparations, so deseparation is a concept for graphs. So we can construct a set of graphs which have the same deseparation. Okay, for those set of graphs, we call them that they are Markov equivalent class. So this is at most we can recover based on the observed data by using the PC algorithm. Sometimes we may also want to know the edge, the causal relationship between each pair of variables. So can we do more? Another very popular and representative method is called the LiNGAM, which is for linear non-Gaussian cyclic graph model. And here the function is a linear function. So this xj is the direct cause of xi, and this is a structure causal model. And here we have to assume that the noise, the exogenous noise, are non-Gaussian distribution. So maybe many of you are not comfortable with non-Gaussian distribution, but there's a reason why we have to introduce this assumption. For example, we have just two variables, x and y, and we assume that x is a cos of y. So if x is a cos y, then y can be written as y equals alpha x plus a noise, and this noise is an independent noise. So if we regress y on x, the residual will be uncorrelated to x, and also the residual actually is a noise. It is also independent with x, and we can draw those residuals here. And on the other hand, if we calculate the residuals when we do regression of x and y, because the causal relationship is that y equals x plus a noise. If we request x and y, the residue contains the information of the noise, and also it is dependent to the target y. Only when the noise is of non-Gaussian, because if the noise is Gaussian, first when we do the regression, so the residue is independent, is uncorrelated to y. Okay, and if the noise is Gaussian, uncorrelated means that also is independent. But if it is non-Gaussian, then the residue will be depends on y. So there's a kind of a symmetric property between the two directions when the noise is non-Gaussian. Then by using the symmetry, we can discover the causal information. This algorithm is called LiNGAM. And here we have the assumption that the noise is of non-Gaussian, and there's some further studies which extended the setting. The noise could be Gaussian, but the function should be nonlinear. And also there's post-nonlinear functions for those structural causal model. But we just quickly skip this. If you are interested, you can refer to those papers. So another setting is that we want to do causal discovery with latent variables. And then also quickly, I will introduce you the high-level idea. There are some assumptions, for example, Markov property assumption, faithfulness assumption. Also, we assume that the structural causal model are of linear functions, and also the noise is of non-Gaussian. There's another somehow strong assumption which assume that for each latent variables, they have no parents, so they are independent to each other. With those assumptions, the problem to discover the causal relationship has a very close relationship to the overcomplete independent component analysis problem. And using the technique developed in the overcomplete independent component analysis, those causal structure can be recovered. Okay, and now you can also feel that those assumptions are somehow strong, especially this one. The latent variables has no parent. Okay, so there's some other work which proposed weaker assumptions. For example, this one proposed in 2016, they assume that there may be some dependence for those latent variables, but for each latent variable, they record that there are at least 3 pure children, which means that for those children, other than this latent variable, they have no other labels, and we call those children as pure children. So with 3 children, then we can identify these latent variables, and further we can discover those causal relationship. So, another work in last year, they have another weaker assumption. They assume that the noise is non-Gaussian, and for each latent variable, even though they are dependent to each other, for each variable they have to have at least 2 pure children for each latent variable. And with those assumptions, here we can identify those latent variables and then further discover the causal relationship. So for causal discovery, there are assumptions that said some of the assumptions can be verified and some are not, and some assumptions are very strong. So we want to introduce weaker assumptions. And this is a work from our group. Firstly, we say that if there is latent variables, we have to have some requirement for those latent variables. For example, they have to have a certain amount of pure children. For example, in the literature, at least 2 pure children is needed. So for us, we also propose a mild assumption. Rather than pure children, we allow that for two children, they can be connected. So for example, here O3 is a pure, if there's no edge between O3 and O4, then O3 is a pure children of 1. But if there's an edge from O3 to O4, O3 is not a pure children anymore. And for O3 and O4, we call it a generalized pure pair. If we, for each latent variable, if the noise are non-Gaussian, and each latent variable has at least one generalized a pure pair as children, and we can also identify those latent variables and further discover the other relationships. Okay, so we just give you the takeaway message. There's some technical details which can be found in the research paper. And so our paper was published in iClear 2024. I mean, very soon. So discover the causal relationship based on purely observed data is a very interesting direction. And the research, I would say that is still at the early stage. There's many settings we can further explore. For example, causal discovery with missing data, maybe with measurement errors, with long tail distribution, with sparse data, and also we could consider the setting that the causal relationship is non-stationary, and also there some human in the loop with some feedback, and we use those information to design more efficient causal discovery method. And also with a recovered causal graph, we can make use of those causal graph to design more efficient machine learning algorithms. And also we can do causal inference to do some reasoning to have some more explainable predictions. And with the causal graph, we can, in our group, we have designed more efficient, for example, self-supervised learning algorithms, domain adaptation algorithms, and learning with noisy labels, reinforcement learning. And I believe that it can do more, because currently most of the machine learning algorithms, they depend on statistics dependence. Okay, they can make predictions, but they cannot make predictions when there are interventions. So causality is really important, and also important for, I believe, for our research. If you are interested for collaborations, please feel free to reach out. Thank you.